more interesting than a blank screen you can barely read. Okay.
Do we need to switch off the light over there, or is it okay?
Can everybody see this? In the early 1980s, here at the university, they had key systems for telephone service. Now what that means is each department had a phone number. And if you wanted to call somebody in a department, you would have to call the department's phone number. The secretary would answer, find out who you wanted to talk to, and then transfer you to that person. Okay? You couldn't directly call anybody on campus.
When was that?
This is in the early 80s. Okay? Now, the university decided that they would get phone service for every employee. So they went to Southwestern Bell and they said, we need to buy some phone lines, and we'd like to get those phone numbers all with the same prefix. So Southwestern Bell said, you betcha. We have the 747 prefix here. And you can have extension 0000 through 9999, which is 10,000 phone numbers. Anybody want to guess what the university replied?
We don't want that many.
Pretty much. And, you know, for them, it was a business decision. They didn't need that many lines. So what they did is they bought the 747 5000 range. Okay? And as the university grew, they went back to Southwestern Bell and bought 747 6000 range, 747 7000 range, the 747 4000 range. And then no more, because Southwestern Bell is a business. And they had other customers who needed lines. And they sold all the rest. So there's a foreseeable problem where there may not be any more 747 extensions for us to use. Now, that wasn't necessarily a bad decision. I mean, over 25 years, that worked out pretty good for the university. So what has this got to do with addressing? Well, in the early 80s, they introduced Internet Protocol version 4, IPv4. This is for addressing networks. They had a 32-bit address, normally written for humans in dotted decimal format. And for those of you familiar with UTEP, you recognize the 129.108. Okay? Now, they made some assumptions when they developed this, that, you know, maybe the military, maybe some government agencies, maybe some research institutions, maybe some education institutions may want to connect. Okay? And then what was it, about 1989, AOL offered their dial-up service. A little bit later, the World Wide Web was introduced. Explosion across the internet, and they needed more and more addresses. Okay? And they realized that there would be an exhaustion of this address space. With 32 bits.
Out of curiosity, I never realized that this is actually the decimal form of the binary address, right?
That is correct.
So how does this 32 bits divided between these parts? The first is the first
8 bits, 8 bits, 8 bits, and 8 bits.
And the /16 has nothing to do with that.
Right. That'll identify what's a host,
okay,
what's a network.
Okay.
So even though they could get 4 billion or so out of that 32-bit address space, they realized there would be an exhaustion. So about 1995, they developed version 6. And they decided on a 128-bit address space. Okay? 8 quartets of hexadecimal for humans. And hopefully sometime in the future here, you all will get familiar with 2001 468 1D80 as being UTEPs. Okay?
That's memorable.
Now, some assumptions they made that would drive this address space is cell phones, handhelds, all needing to be networked. But I'm thinking probably more is the sensor networks that are being developed. You know, environmental sensors in a building. Is it too cold? Is it too hot? Are the windows open? Are the lights on? Is there milk in your refrigerator? All right, sensors embedded in the highways talking to your sensors in your cars about the weather, speed, and all that kind of stuff. All that will have to be networked for communication, and that's probably what's going to be the killer app for this.
Why do we still need /48?
Same reason.
So this is
It's
only
going to identify
addressed to the
what's the
server.
network and what's the host.
So the 48 counts what?
48 counts bits.
So that's the number of bits to specify, leading bits that specify the organization, and then all the rest of the bits are to specify the device.
That is correct.
Oh, okay. Now I understand. Okay.
Now, it's great. Okay, we got all these new addresses. All right. But what's more important is the improvements they did to the protocol. This is what we're using right now, IP version 4. And this is a header for a packet. And what I want you to notice is we have something called identification, fragment offset, and something called header checksum. Packets, as they travel through the network, may be too large to go down some links. So the network device will have to break up that packet into fragments. It's going to have to identify the fragments, identify how to put the fragments back together. Also, for integrity, you know, as these bits go over the network, they may become corrupted. So you have the header checksum. Because what is this header? It is a string of zeros and ones. What does a string of zeros and ones represent? We're all in CS here, right? How about an integer? Okay? If it's a number, I can add 5 to it, divide it by 8, do a 1's complement of it. Whatever I decide to do, whatever the result is, would become the header checksum. So
the checksum is not actually the sum of zeros and ones. It's something else.
it is a function that's done on that string. So, as our packets travel through the network, let's say we have this PCA up here, and he wants to talk to PCB. So, he makes himself up a packet. And let's say he can make an 8K byte packet. So he makes his packet, he's got to compute his checksum, and he sends it to his router. The router is going to verify the checksum. If it's good, if it matches, he's going to accept the packet. If it's bad, he's going to reject the packet and send an error message back to the sender. If he accepts the packet, he's got to route it. He's got to figure out where he's going to send it. So he figures out he's going to send it out here. Well, what do you know? There's a 4K byte limit on that link right there. So what does this router have to do? It has to fragment this packet into 2. It's now going to compute 2 new checksums because the packet is changed, right? And it's going to send them out. This router down here is going to get 2 packets. He's going to verify 2 checksums. Decide whether he accepts them. He's going to route 2 packets. He's going to send them out here. But what do you know? He's got a 2K limit on packets. So what has he got to do? He has to break up his 2 packets into 4 packets. He's got to figure out 4 checksums. And he's got to send it out to this guy. Here, he's going to verify 4 checksums on the 4 packets he gets, reconstruct them, and do whatever he wants with them. We see the load we are putting on these devices. This is very simple. In actuality, there may be 12, 20 routers between a sender and a receiver. All right? And there may be thousands, millions of packets running through a router. Go ahead.
None of the routers ever have enough information to recombine packets.
They do not recombine packets. Once they're fragmented, they stay fragmented until they reach the receiver.
Can I ask a question about the previous thing? So, how is the code, is it the same, how is the code, old code of UTEP, for example, related to the new code of UTEP?
It's not.
Oh, it's not, okay.
There's no
thinking.
equation between the two.
Okay, it's just completely new now.
That is correct.
So how will the transition be happening?
Painfully. This is an IPv6 header. You take a minute. That was what we're using right now. And that's an IPv6. Very much simplified. There's no fragmentation. There's no header checksum. And something new called a flow label. That does not mean that the requirement for checking the integrity of the information has been eliminated. It does not mean that we can now shove as big a packet through, because those links still have their limits on them. All right? Those things, if they're not in hardware, and the electrical engineer no longer has to take care of that requirement, guess who does? What's that?
Sender and receiver?
The sender and the receiver.
Lower level.
Lower level, but it's still going to probably be software, no longer in hardware. Now, the sender has got to figure out in his software, let's say it's a telnet application that they're sending. All right? Before, all that verify and checksum, that was usually pushed off to a driver, or it could be done on hardware in the NIC card of a PC. Now, that has to be written into your application. So, whatever it is that you decide for integrity check, you have to make sure the other end is going along with it. All right? Also, you need to determine the path MTU. This sender has to figure out what's the biggest packet that this entire path will take. Or what's the size of the smallest link. All right? Now there's a protocol written into IPv6 so that sender can figure out, it can question, it can query the network and figure out what's the biggest packet it can send. So now,
Can that change?
In the current network, if it comes to this point, and something goes wrong, it can change the route, right? So now we will not be able to change the route, right?
as in...
Suppose it comes to router A,
All right.
and at this point, the direct path from router A to router B is disconnected, it's blocked.
And it has to go down another path.
It has to go down another path, so what do we do?
For
Because
IPv6 or IPv4?
For IPv4, if I understand correctly, it can just
It'll just keep
fragment
going
again and
on.
keep going. Now we
Right.
have to go back all the way to PCA, or?
That is correct.
Okay.
He will have to go back and figure that out. So, he still wants to send 8K of information, but he has figured out that 2K is his limit on his packets, so he has to send out 4 2K byte packets. He sends it to this router A. Now, the first packet only. He's going to look at it. There's no longer a checksum, so there's nothing to check. He's going to determine where the packet is supposed to go. But he's also going to decide on a flow label, a number. I'm going to call it 5. All right? So that first packet and that flow label gets a number, and let's say that number is 5. He sends that first packet, and he sends a second, and a third, and the fourth packet, and any other packets that come into him, and it's in that flow, he's just going to label them and send them right away. Any other routers down the line are going to look at that first packet and say, you betcha, we're going to accept the fact that there's a flow label on here. And you know what? Every time we see a 5, we're just going to immediately send it on. Because the router usually has to look here, look all the way into here to route. If he has a flow label, he just has to look up to here. Go ahead.
But the router B is going to be getting packets from all sorts of different routers.
And
how do you know they're not going to repeat flow levels?
he has to, that's some bookkeeping he has to do.
Who has to do it? Router B?
Router B has to accept the first
No, I mean, the question is because this is distributed process. Router A assigns flow labels,
Right.
and router C assigns flow labels, and they're not connected.
That is
So what
correct.
prevents router C to assign the same number 5 to a completely different flow?
That's right. If that first packet comes in from router C,
Yes.
the router, say there's a router C, and he decides he's going to try flow label 5.
Right.
He sends his first packet to this router.
Okay.
This router here is going to look at it and say, you know what, this is the first packet from this guy.
How does it know it's the first packet from this guy?
Probably
so it marks
probably
flow.
from where it comes in.
Okay.
But let's say there's 2 paths from 2 different sources. You have 2 different sources feeding to the same route from A to B.
It's to be the direct neighbor.
Okay.
There's not going to be a router here that's going to have a flow label that's not going to talk to this guy and just talk to this guy.
And it's the same flow label the whole way through.
Right. So that there's some housekeeping, they have to pay attention.
Okay. So if the flow number is the same, that it will send the message back to router C.
Right, I
and
don't
give me
accept
another
your
flow
flow
label.
label, give me another flow label. Or, at some implementations, you'll just change the flow label.
Okay.
Okay? The big point is, yes, we have tons more addresses. Okay? More importantly, as you saw the load taken off the routers. That's a big problem now with traffic. Is, if every packet you have to do a checksum, you can imagine, that's quite a load. And if we can voice that off on a higher level, make some software programmers take care of it, get a little better efficiency out of it. Go ahead.
So it's a software program that only takes place at the very beginning and very end of your path. It doesn't take place at every node.
That is correct.
in the path.
That's right.
That seems to be-
Yeah. No questions?
So this is already implemented, or it will be implemented, or what's the status?
I have 2 nodes in all that address space. But I have to figure out, the big thing is, you'll notice how big the numbers are. And can you imagine having to remember or connect to things using numbers? Big thing I'm working on right now is a name service, DNS, so that you can say google.com instead of 2001 something, 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 something.
Does the DNS algorithm change, or you can use the same one?
You can use same software. They've actually just made new entries.
which is an extension of the existing protocol.
That is correct. And so there's some gotchas right now on some OSs. If you happen to be running IPv6 along with IPv4, it just turns on automatically your DNS resolution. It'll go try to find an IPv6 address first. So you'll notice as you explore the little circle, little flags waving in the wind, that's because he's trying to find an IPv6 DNS. And it's not until it times out and says, wow, there's no IPv6 DNS for this name, then it'll go to the IPv4 and ask.
So once everyone goes to IPv6, it'll be faster, but for now we pay a little bit.
Yes.
Yeah. And this offloading of the router, there's another thing I think is going on here too, which is the router's job becomes easier, not just in checking the checksums, but also the computation of where to route the packets through for the path only has to occur once for a stream rather than having to be decided for every single packet that's sent through.
No, but I'm thinking in terms of like downloading the video and watching it in real time. Will that be still doable? Because during the time when I get the video, clearly the path will change, right?
So what's the sequence of events that occurs? Should, let's say, you have a player which establishes a route, a path, and is streaming in video, and along the way some link drops out, and so that path fails. What's going to happen?
Well, normally, if there are two paths coming from a router, if there are two paths to anywhere, that flow would be load balanced between them. So the two neighbors down there would already know about these flow labels.
Okay, so it's not necessarily just one path. It could be several paths.
That is correct.
Okay.
In which case the MTU, the maximum message packet length will have been established for all routes that in the family of routes that are.
And it would probably take and establish for the smallest.
Okay, so thank you very much.